I think that means it's time to start. Once you guys are done eating Skittles or whatever it is. Super different. Not as good.
What do you mean? The orange ones are better.
The orange ones are the best. But.
I'm resting my doctorate class.
All right. Well, welcome to another Monday. Monday number 2. We're going to be. I'm going to be sending out a video to all of you. I think EWB, if you don't know what EWB is, you'll see in the video, Engineers Without Borders. I think this week has their first meeting of the semester. They're looking right now to start up a new project. I don't know exactly what the project is going to be. If you join, you're going to be part of the group helping to figure out what that would be. But it's a really cool group on campus. It's a student-led. It's kind of been engineering-led, but it's not just an engineering group. It is open to people, although it's Engineers Without Borders. It's open to people outside of engineering. It has kind of special, or this class has a special place in EWB because a lot of the projects tend to be water projects for different communities. So a lot of the problems are fluid type problems. Anyway, so I'll send out a video for that, so look for that. And I think that's this week, Thursday, although I don't remember the time. All right, what we're going to be doing today is looking at kind of the second main part, and kind of introducing the second main part of fluids. So what we've done so far is kind of the visualization part, and how do we talk about it, and how do we think about, kind of connecting some of the basic math of velocity fields and some of that. Obviously, there's more to that picture that we're going to continue to flesh out, but that's part of it. The second part of it, so visualizing things, being able to do calculations. The other part is to start understanding how forces work. So if you want to understand motion, you have to understand forces. So we're going to put some nomenclature and some ideas behind that today, forces and stresses. So that's what we're going to do today. The other thing just to announce here at the start is there is going to be a quiz at the beginning of next class. It will be short, so quiz on, what I'll call this like flow visualization. Just a note. So that's going to be, it's going to be like 5 minutes. It's not a long quiz, but it'll test, do you understand the difference between a streamline and a streak line and a path line and velocity vectors and trying to connect that. There'll be like a short video that we watch, and then you'll try to figure out streamlines and path lines and stuff like that from some of the visual stuff that we're going to talk about, or that I'll show. So if you feel like you kind of know those definitions, you're going to be in a good spot, but that's what it's going to be. It's going to be on. So look for that kind of at the start of class on Wednesday. All right, so today we're going to be talking about stresses and viscosity. Kind of to pave the way for understanding how fluids move and how they behave. So if we imagine a little piece of fluid, we can say, okay, so we have some fluid. What types of forces could be acting on this fluid? So let's imagine we'll make it a cube because that will make some of this easier. Let's imagine a cube of fluid. Right, something, not a good cube. Something like this. So this is our fluid. So what types of forces would be acting on this fluid? There are kind of two main classes of forces. But I guess, can you guys think of what types of forces would be acting on our little chunk of fluid that, is presumably floating in, a larger body of fluid? So there's this is a little chunk of water inside of a lake or a river. What types of forces could be acting on it? Yeah, Theo. That's one of the big, one of the categories of force, like specific forces. Gravity is one. So that would be what we would call a body force. Gravity. That's the main body force. The other possible, right? So a body force, and we'll talk about this, that's a force that acts equally throughout the entire cube of fluid. So this is a force acting on entire body of the fluid. The second type of force, the other body force that you can run into, but we never will in this class, would be like electricity, like magnetism. If you have a ferromagnetic fluid, which is really rare, you could potentially have like a magnetic force acting throughout the entire fluid. There are specialized cases where that happens, and that's important, and that's maybe the most important force. But that's kind of a rare, more niche case. But that would be the other force that acts like evenly throughout the entire piece of fluid. So the other class of forces are surface forces. And there are kind of two different surface forces that might be acting on our chunk of fluid. Can anybody think of or name at least one of the two?
Would there be compression because you're blowing on top of each other?
So that would be so there could be a compressive stress, but that would be caused by like pressure, right? So pressure is one of the forces that can act like pushing on the sides of our cube in some way. And then the other one is friction. Okay, so these are forces on the surface. Okay, so you guys have already, because of some of the other classes that you've taken, you've already kind of made the leap to what this does to the surface. It creates some sort of stress, like a compressive stress or a shear stress. So the surface forces, body forces are going to act equally everywhere. Surface forces are going to be pushing on the surface and create some sort of stress. So surface forces lead to stresses on the particle surface. Okay, so this is a little weird, but we're going to be kind of thinking of this as like a little small chunk of fluid. There are going to be stresses that act on the surfaces of that. Okay, so what do those stresses do, and what do they look like? There are two different types of them. There would be something acting, say, in this direction on that, and that would be creating a compressive stress, or what we call a normal stress. Okay, so if we're acting like perpendicular to the surface, that's going to compress it. That's going to be a normal stress. The other one would be if we're acting parallel to the surface, right? Something like this, that would be creating a shear stress. Okay, so if we have forces happening on the surface of our little cube, that's going to be one of these two types of things, or it's going to be a combination of the two, right? It's going to be some, we can like break it up into the different components of the force vector, and we'll have, some of it will be a normal stress and some of it will be a shear stress. So it can be some of each. Okay, so the challenge is, okay, so nomenclature gets, like how we talk about the different shear stresses and normal stresses gets a little bit tricky. Because if we think of our fluid particle, you don't need to draw this on yours, but I'm just going to kind of mess mine up. So we could have a normal stress like that, like I have it drawn. We could also have a normal stress on this side. We could have a normal stress on this side. We could have a normal stress pushing on the front. We could have a normal stress pushing on the back. We could have a normal stress pushing on the bottom, right, on any side of our cube. So that gets a little bit complicated. It gets more fun with a shear stress, because we could have a shear stress like I have it drawn, or you could have a shear stress, say, that way. Or you could have on this side a shear stress, like on the front side, you could have a shear stress up or that way. On this side, you could have a shear stress up or this way. So so how do you differentiate all these different types of stresses? What is like a good consistent nomenclature? Okay, so if we have a normal stress, okay, so this is caused by forces normal to the fluid particle surface. The mathematical definition, right? A stress is a force over an area. So the mathematical definition, I'll write so our nomenclature is going to be sigma. And we'll call this sigma xx. I'll just write it and then I'll put some stuff around so that we can hopefully figure out where this nomenclature comes from. So this would be the limit as dA goes to 0 of okay, force over the area. So again, let's unpack this a little bit. Okay, so this is a force acting in X, right? And kind of these parts just mean like a stress, as we talk about, is a force over an area. So a force acting over an area is a stress. So that's why we have this kind of limit notation and divided by dA. Don't worry too much about that. Stress is force over an area. So here, sigma is used for normal stress. So that's going to be the variable that we use for normal stress. And then our like sigma xx The first one is identifying the plane of action. So identify the plane, and it does this. That's the outward normal. Again, I'll draw this out in a second, and then we'll draw a picture of everything. Okay, and then this other x here is the direction of the force. Okay, so sigma xx is saying that this is the happening in the plane with an outward normal in the x direction. So this is happening in the YZ plane. So this would look like, right, we have, let me draw it like this. So we would have, something like this. This is Y, X, Z. And this is a force say in that direction. Right? This leads to a stress, which we would call sigma xx. Okay. Okay, so it's happening in the it's a normal stress happening in the x direction. Shear stress, they get a little bit weirder. For a shear stress, right? A shear stress is one that's happening in the plane that we're talking about, but we use the same basic nomenclature. So we'll call it tau xy. So this would be the limit of Fy over dA. And we'd say the same thing. So this is identifying the plane. And this is the direction of the force. So that would be a force acting in the y direction on this YZ plane. That would lead to a shear stress that we would call tau xy. So we call normal stresses sigma, shear stresses tau, and then we use these two subscripts, one to tell us which plane, the other to tell us which direction. Just to look at exactly what that looks like. This is a figure from our book. Okay, so we would have a, as I said, so we were drawing kind of this plane, and I'll post these slides so you'll have this picture. We were drawing this plane, so a sigma xx is happening. So this is the x plane because the outward normal is pointing in the x direction. So we would have sigma xx, tau x z, because this is pointing now in the z direction, and tau xy, because this is pointing in the y direction. We will use these. We'll eventually probably get used to them. Maybe we won't, but this is a good picture to just have when we start talking about stresses and stuff. This is a good picture to come back to figure out what exactly is that talking about. But we have really these two different ones. We have shear and normal. they work a lot like solids, right? A shear and a normal, it's the same type of nomenclature that we would use for solids. They're a little bit different because, right, solids are elastic and fluids are not. So if you have a shear in a solid, you know, maybe you would talk about like at what point do you actually get buckling in that solid or something like that, or if you have a normal, what's the deformation? In a liquid, we don't have just like elastic deformation, we have movement. So the challenge for fluids is to figure out, okay, what type of movement do these different stresses result in? And how can we talk about that? So the two types of stresses are fundamentally different because they don't, so if you think about a normal stress, let me go back to here. No, not that. Right, if you think about a normal stress, you're talking about something at the surface, which is either like a compression or kind of an expansion, but it's like pushing in or squeezing in. That's not going to create movement. That's going to, like, if you squeeze a fluid, it might create a volume change. Kind of, it's going to act and look very similar to what we think of like solids acting under a normal or under compressive stress or something like that. But a shear is going to cause movement. So we're going to kind of deal with these both separately. So we'll start by looking at the shear. Probably, we might get through all of that this week, and then we'll talk maybe the beginning of next class and the end of that about what happens when we have a normal stress. So we'll start with shear stress, then we'll talk about normal stress, kind of these two different classes. Okay, so in fluids, shear stresses to deformation or flow, right? If you have a fluid that has a shear stress, that causes it to flow, or it causes it to deform in some way, which is right different than solids. So let's look at exactly how that would work. So kind of our thought experiment would be, and we keep coming back to this because it's the easiest to think about. If we have fluid in a channel like this, so let's call this the y direction, that the x direction. Okay, so what's going to happen if we have our chunk of fluid? So this is our, let me draw this just in blue. So this is our chunk of fluid. So the question is, okay, so how could we apply a shear stress to that chunk of fluid? Well, you move the two plates in different directions, or you keep one still and then you move the other one. So if this is, if the bottom one is stationary and the top one is moving with a velocity u, right, we know this, like the top one is going to move, the bottom one's not. What does that movement look like in terms of forces and stress? Okay, so how does So this would be tau. So this is going to cause a stress in the same direction. So that's going to be on what the plane is going to be on the top plane. So the normal is in the y direction. So this is tau y. And the shear stress is in the x direction because that's where the movement is. So this is tau y x. So how does the velocity relate to the shear stress that we put on that fluid? Right, shear stress being force divided by area. Well, if you look at fluid motion, most fluids, this relationship between like how something like this, how the force would change with velocity, that relationship between force and velocity, for most fluids, it's actually a really simple relationship. For most fluids, it's linear. So if you have two things, with a fluid in between and you're moving it, and say you're applying 10 newtons of force, and that moves it at 1 meter per second. If you applied 20 newtons of force, you'd move at 2 meters per second. If you applied 100 newtons of force, you'd move at 10 meters per second. So for most fluids, that relationship between how hard do you have to push that top plate versus how fast it's going, it's a linear relationship. For most fluids, for what we call Newtonian fluids, Newtonian being like Isaac Newton, for a Newtonian fluid, is proportional to U. And I'll underline Newtonian, right? So what that means is to double velocity we double the applied force. Okay. There's a constant though in all of that. Okay. So if you looked at two different fluids, so you have the same setup, you're applying a 10 Newton force. In water, you move at 1 meter per second. Okay. Okay. If you switched out the fluid for honey, honey's really sticky. Sticky, it's very viscous, would be the word that we use. That same 10 Newton force isn't going to lead to a 1 meter per second. It's going to be slower. So for most fluids, these two things are proportional. The force that you apply, or the stress, and the velocity. But there's a constant that relates the two, right? And that constant is a fluid-specific thing. We call it the viscosity. So Newton's law of viscosity this is where we get this concept of viscosity. So tau yx is equal to the viscosity, which we're going to give the variable mu. So this is what we call the dynamic viscosity. Mu times, okay, so it's not exactly times the velocity, but it's times du dy. Okay, so where does the du dy come in? All right, so that's the shear, what we would call the shear rate. is the shear rate. And if we go back up to our picture, up here, this would be, right, our fluid is going to flow, say something like this. So that slope is the shear rate. Okay, so yeah.
So I'm like a problem with that, like, so we give 2 points and have to find the slope.
It could be either. Yeah, there are different ways to think about that. So we'll do some example problems that hopefully will help. Okay, but so we have this idea, and the way that I think about it, okay, you can think of, what is viscosity and shear and how do all these things fit together? The way I think about it, if you have in this picture, the fluid at the bottom is stopped, the fluid at the top is moving fast. You can think of it kind of like two layers rubbing against each other. So what is the viscosity? Well, it's the friction forces between those layers of fluid that's resisting the motion. So viscosity between okay, so viscosity is going to be something that's physically what it is, right? Like the reason that honey has a large viscosity and water has a smaller viscosity is because like the honey molecules are long and dangly and they get tangled up in between each other, and that causes a friction force because you try to move them and they're kind of stuck together. So that's why. So that is physically what viscosity is. It's the layers of fluid that are trying to slip past each other, getting stuck and kind of tangled up with each other and resisting that motion, resisting being sheared apart. So that's where viscosity comes from. It's these friction forces between the layers of fluid sliding across one another. Just a brief discussion on units. So tau yx is a force divided by an area. So it's going to have something like units of newtons per meter squared, or pounds force per foot squared, something like that. Some unit of force that we've used in other classes divided by an area. That's going to be the shear stress. Viscosity has units of, well, if we look back up at our equation, right, it's a little bit weird, but we have a viscosity times like a slope of the velocity. And that has to give units of force per area, so we could go through and do the dimensional analysis. But it's going to be force times time over area. So that would be one way to do it, but force we can actually like decompose into more basic units. So we could actually write this as mass over length times time. So those are equivalent unit systems, despite the fact that they look different. So we're going to have a number of weird types of units for viscosity. So force times time over area, or mass divided by length times time. So we have, the first one would be something like a 1 Pascal second, right, which is equal to 1 Newton second per square meter, right? Where a Pascal is a pressure, so, which is a force divided by area times time. So Newton per meter. So these are two equivalent things kind of in this first, that first version of viscosity. So you could talk about the viscosity of something in Pascal seconds. The mass divided by length times time is another different unit system. This we would talk about 1 poise, or 1 centipoise. Centipoise is actually the more common version. So you could talk about something, this has a viscosity of 3 centipoise, or 0.28 centipoise. So it's a unit that you might come across. 1 poise is equal to 1 gram per centimeter second. Right, which is a mass divided by length times time. These are, so Pascal seconds and centipoise are the two most common units. You can obviously go back and forth between them really easily with, like, Google a unit conversion, or you can do the unit conversion yourself. But it's easy to go back and forth between them, but these are the kind of two common types of language that you might find somewhere. They vary depending on, like, who's talking and what field you're in, which one is the more common that people use. We also, so viscosity is weird. So usually I call this up here the dynamic viscosity, mu. That's not the only one that we deal with. There's another type of viscosity, and this is where things get a little confusing. We often see the ratio viscosity divided by density. So why would we see viscosity divided by density? So when you're talking about flow, right, viscosity is like friction forces. Density is related to inertial forces, right, inertia. So if something's moving and viscosity is restricting the flow, the inertia is trying to keep the flow going. So this ratio, viscosity divided by density, if two things have, right, the same ratio, in a lot of cases, they'll behave the same because you have kind of the same resistance to flow, inertia ratio. So we often see this ratio. We'll see it come up because we're engineers and we see ratios and we see it a lot. Rather than writing viscosity over density, a lot of times we just simplify it to a single thing. So this is, right, this is the viscosity mu divided by the density rho. And we just call this the kinematic viscosity. Right? Kinematic meaning relating to motion, right? Because you have this like resistance to motion, which is viscosity, and inertia, which is from the density. So that's where this This idea like this is the viscosity version that becomes important in moving things more often. So the kinematic viscosity, we use nu, so this is Greek nu, and the dynamic viscosity is, so if things weren't confusing enough, they're mu and nu. We'll just have to kind of get used to them. These are the terminology that different people use. So, right, you might expect, like viscosity, kinematic viscosity has its own units. So units of nu is an area per time, which is just a weird unit. The most common one is the Stoke, which is defined as 1 centimeter squared per second. You'll often also see the centistoke, which is a 1/100th of a stoke. Again, kind of the world of viscosity becomes this weird thing of all kinds of different units and definitions that will be a little bit tricky to keep apart, especially early on. All right, so right, just some things about the units of viscosity, but then also like what are the types of values that you could see. There are some things that you all know just from your personal experience, right? Like gases have low viscosity compared to liquids, right? If I move my hand through a gas, it's really easy. If I did the same thing in water, it's really hard. If I did the same thing in like corn syrup, that's even harder. Also, viscosity will change with temperature, at least, well, for both gases and liquids. For liquids, right, they get thinner as they get hot. So you can see that this is, so this is the viscosity. This is mu in, this is a chart from our book, but this is in Newton second per meter squared, so Pascal seconds. Okay, we can see like some oils are up here. They're getting, right, a lot, what we would call thinner, a lot less viscous as they get hotter. This is going from -20 C up to 120 Celsius. So you can get the viscosity changing, right? This is changing by a factor of about 100, maybe not quite that, maybe, yeah, a little over 100. So some oils in, you know, going from freezing to the boiling point of water, you might change viscosity by a factor of 100. So some of these things can be really dependent on temperature, how thick your fluid is going to be. There are other things like water. So water does change viscosity as well. This one is water. Water changes in that same, like between freezing and boiling, it also gets thinner, but not nearly as dramatically. It changes by a factor of like 7 or 8 times. So, I mean, it's still pretty significant. So for liquids especially, temperature really does matter for how thick they are and how viscous they are. Gases are much less so. But one of the kind of interesting things about gases is they actually go the opposite direction, right? So liquids get thinner as the temperature goes up. Gases get thicker as the temperature goes up. So gases all have this slope where you get higher viscosity as the temperature goes up. right? And again, this is because of these, viscosity is friction of moving layers. So when you have a liquid, you go to higher temperature, the liquid, all the individual atoms or molecules are moving faster, which makes them kind of slip past each other easier. There's less intermolecular bonding forces. It's easier to overcome those because you have more temperature. Gases, when you go to higher temperature, the atoms are moving faster. They're really far apart, but that means like there are more collisions between the layers of gases. So there's more interaction actually at higher temperature. So you get kind of this weird thing. So liquids get thinner as you get hotter, sometimes a lot thinner, like 100 times maybe. So you really have to know what temperatures you're dealing with. The other, and this is just the last note before we end. So for so new changes with temp for liquids, a lot, and gases. Liquids a lot, gases a little. For liquids, as temperature goes up, viscosity goes down. For gases, again, as temperature goes up, viscosity goes up. So there are values so if you need to find like the viscosity of water, if it's not given to you, there are values, people have measured these. There are ways that you personally could measure them if you're, I've measured viscosity of, I did some work in undergrad with oils and different stuff for calibrating fuel injectors for cars. So we had to make sure that like our mixture was the same viscosity and density and everything as gasoline. So there are little viscometers that you can use to measure what the viscosity is. So it's something you can measure. It's something also you can look up really easily. So Appendix A in our book. There are also in problems in this class, we might find it just, I'll just give you the value or tell you to look it up in a specific table or something like that. Temperature matters a lot. Pressure doesn't so much. So viscosity is only weakly influenced by pressure. So the last note. So it changes, it can change a lot because of temperature, only a tiny bit for pressure. So for example, for water, viscosity at 10,000 atmospheres is about 2 times the viscosity at 1 atmosphere. So for a liquid, you can get maybe 100 times difference in like 100 degrees Celsius. You have to go to like a 10,000 times pressure difference to get like a factor of 2 change. So typically we'll ignore it because temperature matters so much more for viscosity. So you can see bigger differences in some cases, but in most cases, temperature wins versus pressure. That is all for today. So we'll end there. On Wednesday, we'll come back and we'll do some example. We'll do at least one example problem with this, looking at how we can use all of this stuff together. But there's also, just remember that quiz at the start of class. So have a good week.